Hi, everyone. I'm Samantha Bruce. I'm the Digital Marketing Lead at Typhoon HIL, and we'll be moderating today's webinar on automating interoperable grid support function testing in a controller hardware-in-the-loop environment. This webinar is co-hosted with Sandia National Lab and the Austrian Institute of Technology, so it'll be pretty exciting today. So for most of you who are not familiar with who we are, we provide ultra-high fidelity simulation for power electronics and power systems. And today we have very special guests. We have Jay Johnson, Principal Member of Technical Staff at Sandia National Labs. Sandia is one of the largest Department of Energy labs in the U.S. And we have Zoran Milecic, Senior Electrical Engineer from the Austrian Institute of Technology, a leading research and technology institution doing R&D in key infrastructure issues. So here's a brief overview of what we'll be going today. First part, we have short Q&A presentation on the bigger picture. What are the challenges of developing and testing DERs? Why DER certification is very important, and what are the major advantages of using a controller hardware-in-the-loop platform to design, test, and certify smart inverters. And then we can go ahead and talk more about Zoran's AIT Smart Grid Converter and how they've used this technology to design and develop their inverters from scratch. And then it will be followed by a live demo of simple inverter functionalities in a C-HIL testbed led by Jay Johnson, where we'll be showing you guys a live demo of how you can use this platform to test simple inverter functions like power factor, volt-var, frequency watt, and curtailments. And then at the end, we have a live Q&A session. So I'd encourage everybody to pitch your questions. You'll be able to see on the right side of your panel some questions panel. So please go ahead and write that down. We have engineers that can help you answer that question. So before we begin, I'm just curious of what application is everybody coming from, and we have a few options here. So please let us know if you're mainly interested in battery storage, solar, wind, drives, microgrid, or other applications. So you can get a better feel of where everyone's coming from here. So it looks like most of you, 70% are in microgrid and 70% in solar and wind. I'm not sure how they did that. So microgrids and solar and wind and battery. Perfect. Thank you for joining us. I think it will be pretty exciting. We'll be mainly talking about those applications and how you can use this to design your battery storage, solar and wind and microgrids. So with that in mind, I'm going to go ahead and switch the presentation over to Jay Johnson and ask him what are the major challenges smart inverter manufacturers are facing when developing, testing, and certifying their inverters.
Yes, thanks very much, Samantha. That's great. Can you see my screen?
Yes, we can see the PowerPoint slides. All
right, let me switch this around. Okay, great. Hopefully you see the full screen presentation at this point. We have a couple of slides that we'd like to go through here at the beginning just to provide some context, but the majority of our talk today will be the live demonstration. But I think it's good to understand why we're doing this work and what the importance is at the global scale. And so especially worldwide, but in the United States too, we see that the costs of solar energy are declining and continue to decline. And with that, there are additional penetrations of renewables on the distribution and transmission power systems. As you add additional PV and other DER devices to these systems, we encounter technical challenges both at the distribution and transmission level. At the distribution, primarily, we're concerned about voltage regulation, and at the bulk level, we're concerned about frequency regulation. So unless we can mitigate these challenges, we're going to reach a limit or some sort of cap to the total PV penetration levels on these feeders. And so we want to come up with solutions to solve that issue. One of the solutions, as opposed to, say, purchasing expensive equipment like LTCs or cat banks or other equipment to provide additional protection, is to employ advanced inverter features, sometimes called smart inverter features. And these provide voltage and frequency regulating output features. They are tolerant to grid disturbances, and they interact with the power system through communications. And so that's that interoperability component, or the communication side. The United States has recently updated in 2018 the IEEE standard 1547, which now includes new grid support functionality and communication requirements. And so we feel that there is an important need for standardized certification testing of these features, both the electrical capabilities as well as the communication capabilities of DER devices. And so in the United States, we're updating IEEE standard 1547.1 to include a very specific test sequence to evaluate and certify these different grid functions. And it ensures the equipment will operate as anticipated in the field. And by running a lot of different test cases, we can inspect what we would consider like corner cases or specialized situations where you would have like very high or low power factors, or maybe odd volt VAR curves that are very steep. And we can analyze the behavior of the device to make sure that it behaves as anticipated. And this provides DER vendors with confidence that their equipment will function as it's designed, and it provides grid operators confidence that the equipment is going to work as intended when it's connected to the power system. In the Smart Grid International Research Facility Network, or SURFIN, a great acronym, we have an international collaboration of national and research institutes across the world. And these institutes are working on developing automated test scripts for different certification test protocols, like 1547.1. I am going to present some of the capabilities of a software that the group is working with called the System Validation Platform, but I'm not going to be running the 1547.1 tests currently, just because it takes a long time. So I'm going to be demonstrating some of the functionality, but not the precise testing. And so this software that I'm talking about, the System Validation Platform, is a means of scripting automated test procedures in a Python environment, where you communicate, as shown here in the lower left, to grid simulators, PV simulators, the device under test or equipment under test, and a data acquisition system. There can be other components added, but this is generally the structure that's used. And so by communicating to these devices, say you wanted to run a volt VAR test on a DER device, you could set the volt VAR function in the EUT and then adjust the voltage using the grid simulator to ramp up and down that grid voltage to show that the reactive power contribution changes with grid voltage. And the power of the SVP is in that we have created abstraction layers so that any laboratory around the world can use the same testing logic or test script that exists at this high level. You set a series of test parameters that indicate what types of equipment you have for the grid simulator, PV simulator, and data acquisition system, and the device under test. And these can change between labs. So for instance, here at Sandia, we have a lot of Amatec equipment. We've got an Amatec grid simulator and an Amatec PV simulator. And so we can select that device in the abstraction layer, and it points to a specific driver that will change the voltages there. In the experiments that we're going to be conducting today, we're going to be communicating to the Typhoon HIL system, and so there is a Typhoon API that's used to communicate to the simulated grid simulator and the simulated PV system through their API, and we can make those adjustments there. And so the same goes for the other laboratories. We can adjust their equipment, whatever hardware they have, if we have the driver. So specifically, this is how this setup works. So we have the SVP shown here on the left, and so it's going to be changing the grid settings, the PV power settings, and pulling data acquisition measurements from the Typhoon system. It is connected here to the equipment under test, which is in this case is the AIT Smart Grid Converter, and we can communicate from the SVP to their SunSpec Modbus server inside that device using a TCP connection from the computer here. And so this approach of using controller hardware in the loop has a lot of advantages over a large power system test. For one, you can test, in this case, a 34.5 kVA DER device with a simple, benchtop system that has low voltage and low current, and so there's no safety concerns there. It allows for very quick iterations on the design of this, either the communication server or the power electronics and controls here. We can certify or closely show that the certification procedure will be passed when we build the full version of this, because we've got all the same controls inside the control board, and it allows for very rapid iteration. So if you see a problem, you can fix that very quickly and just push that new firmware to the device without risking, say, damaging equipment. So I think there's a lot of advantages to this approach. And so now I'd like to turn this over to Zoran to talk a little bit more about that device under test that we'll be demonstrating today.
Perfect. Thank you, Jay. Before we move on ahead, let's give Zoran some time. I'm curious of where everybody is coming from again, and whether you are already using hardware-in-the-loop technology. So go ahead and answer if you are or not. Great. So it seems like more than half of you have used it. So that's great to know. But also the other half who have not, I think you will have some really interesting insight on how this technology has actually been used in various applications. As we will see in a few moments, Zoran will be showing us how they've used hardware-in-the-loop technology to design and develop and certify their inverters from scratch. So with that in mind, we're going to go ahead and switch the presentation over to Zoran.
Well, hello everyone. First of all, I would like to extend a warm welcome from Vienna on behalf of Austrian Institute of Technology. At Austrian Institute of Technology Power Electronics Group, we research various power electronics subjects. We do the design validation testing, pre-certification, also product development and new product introduction for our customers. So what you see on this slide is our reference project. So this is entirely C-HIL developed and tested power converter. It is called Smart Grid Converter. On the right side, you can see specifications in the nutshell. This converter is different than most of three-phase converters by having a fourth phase, and as such, it is suitable for some applications such as grid-connected energy storage system, grid former, and applications that are listed below, such as PV inverter, active front end, active harmonics filter, and for different defects applications. On this slide, we can see a smart grid converter C-HIL model. In this demo, we will present three-phase operation only. And so we have a powertrain, which is shown in the red circle. This is standard three-phase, three-leg NPC topology converter. On the left side, we see a model of PV generator. And on the right side, a model of grid with variable impedances, transformers, etc. And in some test cases, we also use model of our low voltage ride-through container that is used for, let's say, certification of inverters in our lab. And probably this slide is most relevant and most important because it shows in A, SGC HIL connect or C-HIL application. On the right side, in a red rectangle, you can see a control board. A very same control board is connected to our converter, and basically the only difference is that powertrain, power sources, and let's say grid is being modeled in a HIL environment as opposed to real system. Everything else is quite the same.
Okay, so I've got a couple last slides that I'd like to present that include some results from a couple of papers that we wrote. These show the behavior of the controller hardware in the loop system for different advanced grid functions. The leftmost here is a connect-disconnect command, and so you can see the connect-disconnect signal is this dashed black line. So when we request the device connect, it takes a little while for it to resynchronize with the grid, and then it ramps up the power. And then when we disconnect, it disconnects very quickly and turns off. The middle image here is a active power curtailment command. So we provided full irradiance for the PV system such that it can produce the full output power. And we take steps of 10% to ramp up active power and then ramp it back down 3 different times. And then on the right is a series of different power factors for different irradiance levels. And you can see, in this case, the DER device has a very wide range of power factors that it can use. And so it is a full 2-quadrant, and actually with energy storage, a full 4-quadrant device. So I think the thing everybody wonders about is if the controller hardware in the loop results actually match what the physical device will perform or do. And so we've written a couple of papers looking at that question. And so you can see a comparison between the curtailment function for the controller hardware in the loop system and the physical system in the upper left. And so you see there's very good agreement. At the top, there's a little discrepancy in the maximum power point tracking, but otherwise it's very well aligned. For frequency watt, you can see the controller hardware in the loop results here as we ramp the frequency, and you can see the actual power levels for the lab tests and as the red dots. Volt watt, again, pretty similar, a little different slopes and some hysteresis with the lab test, but otherwise very nice alignment. And even the voltage ride-through tests are very closely matched in terms of their voltage and current levels. And so at that, I think we're good on time. And so I'd like to transition over to a live demonstration of this system.